So welcome everybody. And a big hand please for our speaker, Mr. Laura Berko.
Thank you and good morning. Okay, so the title of the talk is a bit of a misnomer because we will talk a lot about init systems and a little bit about S6. We do not have much time, so we will skim. It will be very superficial. I will be asserting lots of things. So if you have questions, please come talk to me after the presentation, and I will be able to explain and dive a little deeper. But here, we will not have the time to go deep. Let's start. Show of hands. Whatever your init system, be it systemd or anything else, are you happy with it? Raise your hands if you are happy with your init system. Okay, hands down. If you are not happy with your init system, please raise your hands. It's a wash. It's a wash. I still say that it could be perfected. It could be 100%. Why are there still people unhappy with their init system? It's because no init system, be it a traditional one or one of the new ones, has been, I dare say, properly designed. Let us change that in this talk. No less. So what is an init system in the first place? The problem is that init is a very overloaded term. It's vague terminology. The init wars actually happened because nobody had a real clear vision of what an init system is or should be. So I postulate that there are 4 elements to an init system. The first element is sbin init, which is the first process that the kernel actually runs at boot time. The second element is PID1, which is the process that runs as process 1 for most of the machine lifetime. It does not have to be the same program as sbin init. For instance, in embedded devices, sbin init is often a shell script that does a few things and then executes into a big application that runs as PID1 for the rest of the machine lifetime. The third element of an init system is process supervision. We will talk about that. The fourth element of an init system is service management. We will also talk about that in a later slide. Those 4 elements do not necessarily have to run in the same process. You can have all of these parts scattered across processes. This is not often the case. It is the case with supervision suites and service managers. So let us define process supervision. A long-lived process, a daemon, is supervised when it is spawned by the supervision tree, which is a set of stable, long-lived processes started at boot time by PID1. Often the supervision tree is itself reduced to PID1. For instance, with systemd or with system 5 init system, the supervision tree is just init, and it supervises processes directly. So supervision is a good pattern. You do not have to take my word for it. Just I can explain that later. The service is stable and launched in a reproducible environment. The fact that the services are launched in a reproducible environment is a vital point. Only the big guys, systemd and friends, and supervision suites do that correctly. Traditional init systems do not. And this is one of the main arguments of systemd against system 5 init. Is that you need a lot of boilerplate to be able to launch your services in a kind of reproducible environment, and not even then. And it's a fair argument. It's true. Of course, process supervision only applies to daemons, which is long-run processes. Short-lived services do not care about supervision. What is service management? So by definition, a service manager is the program that handles the machine state. At boot time, it brings all the services up. At shutdown time, it brings all the services down. More generally, it brings the machine from one state to another. You have an example of that in System 5 init with run levels. Run levels are a primitive way of managing services. Run levels are a set of service states. When you change run levels, some services go down, some services go up. You change states. What are services? Well, they can be one-shot. They can be one-shot, which means short-lived programs with side effects. For instance, set the system clock, or bring up a network interface. They also can be long runs. Does that work? maybe it's me. They also can be long runs, which means daemons. SSHD, syslogd, whatever. As long as the daemon is up, the service is up. All services, be they one-shot or long runs, have dependencies. And it's the job of the service manager to actually enforce those dependencies. What does that mean? If A depends on B, then there should never be a state for the machine where A is up and B is not. Else it doesn't work. If you do not have that enforcement, it's not a real service manager. So, given the inits we have, what features do they offer? So, on the one hand, you have the big guys, the integrated init systems. Systemd, launchd, upstart, maybe some others. They offer all the 4 elements in one package. sbin init, PID1, process supervision, service management. They also offer much more, which is the main problem of integrated init systems, is that they do a lot more than the 4 elements, and all the rest is out of scope. On the other hand, you have your traditional init systems, system5 init, BSD init. They offer an sbin init, a PID1. They offer a primitive way of supervising services via etc inittab for system5 init, or via etc gettys for BSD init. They also have a service manager, but it is not included in the init package. It comes with something else. It comes as a bunch of shell scripts. For system5 init, you have system5 RC, and for BSD init, you have etc RC, which is the service manager. Those are generally a bunch of scripts that perform service startup and shutdown. And dependencies are manually enforced by the administrator in the file system. I have listed 2 other examples of things that pass as an init system. OpenRC, which is well known. It's am I hitting that? OpenRC, which is not really Can you hear me?
Maybe you can
yeah, that will be better. Okay, so OpenRC, which is not an init system, it's actually a service manager with some attempts at supervision, but you also need an init program to go with it. I have also listed Epoch, the Epoch init system, which is quite similar to System5 init and System5 RC bundled together. It's a new approach of the implementation of System5 init, but it does not question fundamentally the design of it. OpenRC, same thing, is a new approach to the implementation of a service manager, but it does not question the design. Okay, so this is something completely different. This is the Daemon tools family, which you probably have heard of if you're here to listen to this talk. The problem with supervision managed by etc inittab, as in System5 init or BusyBox init, is that it is impractical. It's very static. And nobody uses it for anything else than the gettys. If you look at your default etc inittab, you will see some lines to boot the system and actually the service manager. You will also see lines for gettys and not much else. This is the stock default configuration, and nobody ever changes it. There is a reason for it. It's impractical to change a service. To add or remove a service, you have to edit the file, then send the signal to init. It's hard to make it work. In 1998, Daniel Bernstein, DJB, wrote Daemon Tools, which is the first project offering flexible process supervision. It is the grandfather of all supervision suites. And for the first time, it was realistic to supervise all your daemons on a system with it. So later on, of course, it was imperfect. It was a pioneer. So later on, there were other attempts to improve on that. There were, for instance, daemontools-encore. There was runit, which is probably today the best-known supervision suite. There was perp, which is less known, but it's still part of the Daemon tools family, and it works. There is a 6. All of those are supervision suites. I have also added a word for nosh, which is a suite of tools, which is very similar to S6. Go check it, have a look if you're interested. The problem is it's in C++, so it's quite different from all the rest, and it's less economical. The problem with supervision suites, which are sweet, but not that much, is that they are only 1/4 of an init system. A full-featured init needs all 4 parts and nothing more. Runit provides an sbin init and a PID1, but it does not provide a service manager, for instance. And there is an initiative in Void Linux, the distribution Void Linux, to use Runit as an init system. The problem is it doesn't have a service manager, so they sometimes need hacks to make it work with one-shot services. The hacks are longruns that do nothing. So let's talk about S6, since we have 4 minutes left now. S6 is a supervision suite. What does it also provide? It provides a portable PID1. It provides hooks for service manager integration. There are today 2 service managers that are designed to work with S6, ANOPA and S6RC. And those work on top of S6. They are not integrated to the supervision suite itself. It's a different set of programs that is designed to work on the hooks that S6 provides. So, for now, we are lacking an sbin init program, which is the last element in an init system. The problem is that S6 is designed to be portable, and sbin init cannot be portable because it's highly system-specific. So the approach that we have is we create automatically a script that is suitable as an sbin init program, and the way we create the script is dependent on the operating system. So for now, we have that for Linux. I'm welcoming contributions for other operating systems. Just a word about the technical aspects of S6, because that's why it makes a difference between it and the others. So I postulate, you do not have to take my word for it, that S6 has been designed right. The modularity and layering of the different layers has been done right. S6RC, the service manager, is a parallel service manager, whereas most of the other ones, OpenRC mostly, and Epoch, for instance, start and stop the services serially. S6RC is the only service manager that provides a reproducible launch environment, which we saw it was a necessity for daemons, but it also does it for one-shots. It's the only one that does it. It's portable to any POSIX system. S6 is pure C. All the dependencies are controlled, and it is easy to bootstrap. Just to configure and make, and you're done. S6 uses notification. It never polls, so it's usable in energy-constrained environments, such as in embedded boxes and devices. It's lightweight. It uses 2 megabytes of disk, which is not light, but its disk is cheap. And as far as RAM and CPU are concerned, which are the real scarce resources, it uses practically nothing. You can test it. And I have numbers. You can talk to me after that. S6 is made of very little code, and it has extremely short paths. If you strace systemd from the boot phase, and if you strace S6, you will have a very, very different listing. So, how can you use it today? So S6 is packaged in all good distributions. As mechanism now, not as policy, which means that you will have the programs package. You will not have a supervision tree run and services running with it. For now, you have to do that yourself. S6 is used today as PID1 in a lot of Docker containers, especially with the S6 overlay package, which was made to help you use S6 svscan, which is the root of the supervision tree for S6, as PID1 in your container. The service manager integration with the distribution requires support and joint work with the distribution. So that is what we are doing now, and we are going to do in the foreseeable future. There are plans to make S6 and S6RC an alternative to BusyBox Init plus OpenRC in the Alpine Linux distribution. Okay, so if you want to learn more, you have those links. We have a channel on Freenode. I have a Twitter. And please come to me right now after the presentation, or tomorrow. I will still be here. Thank you for listening.
Thank you very much, Laura. I think we have time for a couple of more questions, but I'm going to hand you back this mic so we can use the other one to hand around.
Cool.
So anybody, any questions? Please raise your hand. So if we have no more questions, then